Hi guys, welcome back to the second part of the second tutorial. Good to see you again here in 10 minutes for Six Sigma. I hope you had seen the first part of this tutorial. Unfortunately, it was a little bit more than 10 minutes, so let's hurry up to make at least this part in 10 minutes. The first part was about description of tolerances, how we come from the tolerance to a KPI, and now I would like to deepen here some aspects. So now we know how we could describe the tolerances a little bit more precise and to make clear and transparent what are our expectations. So now let's go into real use cases. We see here a real use case from Tres Cantos. It's about a normal plastic bottle which we label every day. Here in this case it's the standard 20 headstand bottle with a transparent no label look label. According to the specification, we label this with a tolerance from ±2 mm, and now marketing wanted to bring on a label which is not transparent anymore, means it's not a no label look anymore. You could see the label and the placement of the label, and they asked for a tolerance from ±5 mm instead of ±2 mm. So this was the question, and then the colleagues in Tres Cantos had thought about this and analyzed the situation. So we are in the analyze phase here, and they measured the result of the labeling. The pictures here are out of Minitab. This is a statistical software. So what do we see here? Here in this field, we see that we have a tolerance from ±2 mm, and we see that the mean of the label result measurement is 0.02 whatever millimeter. I mean 0.02. This is the process is perfect in the middle. This we see already out of the figures. Then the number of samples was 373, and the standard deviation of the process was 0.47 or so millimeter. Whether this is good or bad, sounds not so bad, but let's see. So, and the outcome, this we see then here, is that we have the CP left, CP right, what we just had in the tutorial before. The CP overall is 1.41 and the CPK is 1.40. This is the topic with the left and right hand and the shifting process. But here we have just seen that the process is quite good in the middle. So the difference between CP and CPK is very small, what we see here as well. And now we know we want to have a process better than 1.33, and here we have a CPK from 1.40, means everything fine. We have a stable running process, and we could be satisfied with this. But now the question was, what happens if we reduce the tolerance from 2 to 1.5 millimeter? So we take the same database and put in 1.5 instead of 2 millimeter. And let's see what happens. So, and then the mean and standard deviation, everything is of course the same, but our process capability, the CP and CPK, goes down. It's clear because the tolerance field is now smaller, and we have now a CPK from 1.04, and this is below 1.33. Means when we think now in number of bottles which we cannot use, which we have to scrap, then it's a process which is not stable and which we shouldn't do. Means the answer to marketing is, of course, no. We cannot. This is, with this what we have here, not possible. Good. I mean, it's clear, and it's a good answer because there is also the reason behind, and everybody could show and understand why is it so. Here we see a very similar example from Waldheim. The table here is Excel based. It's not Minitab. It's an Excel based tool. It's easier, of course. Minitab is special. Not everybody has Minitab, but Excel, of course, we have, and there is a template. I can also send out to you the template, which you can use. So, and I was discussing with Marco the CPK topic because I wanted to have this in the URS, and Marco had to agree to this, and they thought, this is a CPK, and what is it exactly, and we don't know, and there were no experience, and so we used a machine, or Marco used a machine in Waldheim, and they figured out where are we with our CPK and with the tolerance, and how exact is the machine running. They hadn't checked this before, so, and they made this here in this Excel sheet, and we put in here the tolerance plus minus 2 millimeter. Here are the measurements, and here we see number of samples 200. We see the mean 0.58. We just have in mind what we had in Trescantos. Trescantos was the better, means here the process is not in the middle. This we see already out of the figures without deeper analysis. And the standard deviation is 0.31. This is better than this what we had just in Spain, but the process here is not in the middle. So what do we see here now with the CPKs? And so we see that the CP is 2.16. This is perfect. It's better than the CPK from 2 is better than a Six Sigma process. This is perfect, but the CPK is lower. This is because of the process is not in the middle. So we have one very good right hand side and one not so good left hand side. We take the worst of the two. It's still better than 1.33, but we could improve the process to readjust a little bit the machine to take care that the mean is around 0, and then we have also a CPK better than 2. So let's put in here also the smaller tolerance with plus minus 1.5 millimeter. All the rest stays the same, and now we see that the CP is still higher than 1.33, but the CPK is now below. It's around 0, and this is not what we want to have, but we see that the CP is higher than 1.33. If we would center the process, we would have a stable process, and we could run with this machine also a tolerance plus minus 5 millimeter with a CPK better than 1.33. So I mean it's a good output, and it's interesting to know, and it's also interesting to know that to middle the process is very, very important. And Marco is working on this to automate this, to center the process, so that we have then no difference between CP and CPK, or let's say we have only a small difference, which of course helps. So this is a typical use case, but let's see what do we have additional. So in the analyze phase, I want to show you the Ishikawa, the cause and effect matrix, and the Pareto diagram. And this is important for, in the statistics, we have the questions: has something influence and is something significant? These are the core questions. And what has influence? For this we could use very good the Ishikawa. For what has which influence, we could use the cause and effect matrix. And to make this transparent and visible also for other people, we could use very good the Pareto diagram. And this I would like to deepen now. So here we see the Ishikawa. We stay with the example labeling. We had the whole time we have spoken about labeling. Let's keep this example, and core question was, what has influence? So we could now divide the process in machine, people, material, measurement, methods. So, and here are the inputs, and the output, the y at the end, is our label variance, and this we want to improve. So the question is, what has now influence? There are a lot of things which has influence. The tolerance of the label head, the adjustment of the machine, say the speed, the cycle time of the PLC, the capability of the technician, the humidity, the temperature, the stiffness of the liner, the packaging tolerance in general, the camera system, the application point, the wiper, and whatever there is. When you work out in a team what has influence, you come very fast to a lot of things which have really influence. So at the end, you know now what has influence. But the question is, what has the main influence? What are really the driver, or what are the vital views? For this, you put everything out of the Ishikawa into the cause and effect matrix, and now you think about what has really high influence and what has maybe less influence. So also the labeling, so the adjustment of the label head and the wiping point has higher influence than the cycle time of the PLC, for example. Yeah? So and here you can divide from what is less and what has really high influence. You discuss this with the experts and everybody, and so you can filter out what are the drivers. And the drivers you can put in then into a Pareto diagram to make also visible where are the drivers. So and here you can see, for example, that the adjustment in combination with people capability are the drivers. So when you summarize also a little bit and cluster this a little bit deeper, then you see in the Pareto that the adjustment and the people are means the knowledge of the technicians and the operators. These are the drivers for a good result in the labeling process, and the cycle time of the PLC has also a small influence, but this is not the driver, and it's not the first thing where we have to take care about. So, and when we we analyze this, and when we know what are the drivers, we know also what we have to improve and where we have to improve. And when you figured out where are the improvements, and when you do this and you make then different trials with something what you changed the application point, or maybe you change also a part or a complete system, or you make a change in the program, whatever, you change something and then you make a trial and you change again something and you make again a trial, and so then you get a picture like this here. Yeah? You make trials and you get a result, or you get a lot of results. And the question is then, is there a significant change, or is it more or less the same? So, and well, what we have just seen from the different trials, so I made here out of this also a box plot, and I made a small table where we could see from the different adjustments, the different new settings, the results. So we wanted to have a CPK better than 1.33, and we came from 1.11. So, and we see that this is more or less dancing around the 1.11. Sometimes we are better, sometimes we are not so good. And yeah, also my stomach tells me this is more or less everything the same. This is so minor that this is not significant. But we are here at Six Sigma and we want to know and not to ask our stomach. Means we have to analyze this a little bit in deeper. So for this we have statistical tools and methods in Minitab already, and there we can put everything in, and then we can ask Minitab, how is it? Let us know. So I mean, of course you have to know how and where and so, but Minitab makes then can analyze this, and what we see here, well, what already our stomach told us, that the overlapping, there are big overlappings of the intervals, means there is no difference. It's more or less the same, and the variances are coming from, they are happening by accident. So, and is this now everything? No, unfortunately not. Some things are missing. So I mean, the question is, how do we really do this during FAT or SAT or whatever? And when we measure something, we have to take care about this what we measure and how we measure. So we have to make a gauge R&R. We have to consider the shifting of the process from the short trial into the, what does it mean really in long term, when we have different shifts, different people, different colors, different whatever. So and when we want to measure something, when we want to generate measurements and figures, so that we have to ask ourselves, how shall we measure this? And this is the topic design of experiments. Also means there is a lot more which we could consider and which we could now deepen, but we have already a good starting point with this what we just discussed. But I would like to go a little bit deeper into the gauge R&R, repeatability and reproducibility, difficult word, of the gauge. So we are still in the labeling example. So how could we measure the variations of a label? We could measure this manually with a sliding caliper, no? But I mean, it's clear it's not very exact. Or we could make this manually with a gauge, but it's also inexact. The best solution we have for the time being is with a camera. But the question is, how reliable and how exact is a camera, and this what we measure, this should be at least 10 times better than this what we want to figure out. So also we have to know how exact is the camera. In this case here we could measure the same bottle with the camera, and then let's see what is the outcome. And normally the standard deviation should be 0 when we measure 10 times the same bottle, but of course it's not. There are deviations, and here we see that when we measure the same bottle 10 times, then we see that we have a standard deviation, but the standard deviation is 0.04, and the process we have seen there, we had the standard deviation from 0.49. Also it's more or less, it's the camera is 10 times better than this what we want to know, and this is okay. When this is 10 times better, we can say it's fine. There is no influence. If the camera had also the same standard deviation, then you can forget the result. And and you can add up the standard deviations, not just one standard deviation plus the next. Unfortunately, you have to create at first the square out of this, called variance, then, and then you can add up this. And of course, when you measure something, you have to ask every time, is it a normal standard deviation, standard distribution or not? But we see here in this case, yes, it's fine. So, by the way, where we are just speaking about normal and standard deviation, we are also quite often speaking about mean time to recover and mean time between failure. And here I would like to point out that we have here not a normal standard deviation. We have curves like we see here. They are skewed, right or left. Skewed in most of the cases, it's a right skewed curve, and this is coming from the fact that let's assume we have a small machine, a cap unscrambler, and we want to know the mean time to repair or recover. So the machine is working, and once in an hour you have a small stop, and the time to repair is maybe 2 minutes. So, and this happens once in an hour. Once in an hour you have a stop, and you need to repair or to recover the machine in 2 minutes. But once in a day it needs 5 minutes, and once in a week it needs maybe 10 minutes, and once in a year the motor is broken and it needs 1 shift. But it will never need minus 5 minutes or so. This cannot be, and due to this we have every time a curve like this here. And here we can calculate the mean, but the rules are different here. We don't have a standard deviation, all this kind of things. We have to take care that this is a different curve, and that this is not like a normal Gaussian distribution. So this only by the way to have this in mind. Yeah. So, and now we are already at the end of the second tutorial, from the second part of the second tutorial, and I hope it was interesting. I hope as well that we made this in 10 minutes. I don't know exactly, but let's see. And yeah, and I hope that we see each other again in the tutorial number 3 and number 4, where we speak also about the control chart and other very interesting things. So stay curious and thanks for listening.